Routing Protocols. Lecture number 6. Obaid Khan. Routed Protocol Definition. Routed protocol, used to transmit user data, packets, through an internetwork. Routed protocols are assigned to an interface and determine the method of packet delivery. Examples: IP, IPX, AppleTalk, DeepNet, Banyan Vines, SNMP. Routing protocol definition. Defines logical addressing. Routing protocol, any protocol that defines algorithms to be used for updating routing tables between routers. Basically, a routing protocol determines the path of a packet through an internetwork. Examples: RIP, RIP2, IGRP, IGR, OSPF, ISIS, BGP. Approaches to routing: distance vector routing protocol. Link state routing protocol. Distance vector. Also known as distributed Bellman-Ford or RIP, routing information protocol. Each node, router or host, exchange information with neighboring nodes. Neighbors are both directly connected to same network. Node maintains vector of link costs for each directly attached network and distance and next hop vectors for each destination. Requires transmission of lots of information by each router. Distance vector to all neighbors. Contains estimated path cost to all networks in configuration. Changes take long time to propagate. Distance vector algorithms. 1. Dest. Next. Metric. B. 2. 1. D. A. C. D. B. Dest. Next. Metric. 1. C. 2. D. 3. A. Dest. Next. Metric. C. 3. B. 2. 1. B. A. Dest. Next. Metric. 1. C. D. 2. Distance vector algorithms. 2. Node A will learn of node C's shorter path to node D and update its routing table. A. Dest. Next. Metric. 1. B. D. A. C. D. B. Dest. Next. Metric. 1. C. D. 2. B. Link state algorithms. Used Dijkstra's algorithm for shortest path. Each node shares its link information so that all nodes can build a map of the full network topology. Link information is updated when a link changes state, goes up or down. Link state determined by sending small hello packets to neighbors. Given full topology information, a node can determine the next best hop or a route from the source. Link state algorithms. 1. AB. Link. BC. CD. AB. Link. BC. CD. AB. Link. BC. CD. A. C. D. Assuming the topology is stable for a sufficiently long period, all nodes will have the same topology information. B. AB. Link. BC. CD. Link state algorithms. 2. AB. Link. BC. CD. AC. AB. Link. BC. CD. AC. 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 AB. Link BC CD AC A C D AC B AB. Link BC CD AC. Nodes A and C propagate the existence of link AC to their neighbors and, eventually, to the entire network. Comparison of distance vector and link state routing protocols. Entire routing table is sent as an update. Distance vector protocols send periodic update at every 30 or 90 seconds. Updates are broadcasted. Updates are sent to directly connected neighbor only. Routers don't have end-to-end visibility of entire network. Routing loops. Link state. Updates are incremental and entire routing table is not sent as update. Updates are triggered, not periodic. Updates are multicast. Updates are sent to entire network and to just directly connected neighbor. Routers have visibility of entire network. No routing loops. Convergence is fast because of triggered updates. Static routing typically used in hosts. Enter subnet mask, router, gateway, IP address. Perfect for cases with few connections, doesn't change much. For example, host with a single router connecting to the rest of the Internet. Internet. R1. IP. 128.1.1.100 H1 H2 H3 for H1 next hop 128.1.1.100 Dynamic routing. Most routers use dynamic routing. Automatically build the routing tables. As we saw previously, there are two major approaches. Link state algorithms. Distance vector algorithms. First, some terminology. As equals autonomous system. Contiguous set of networks under one administrative authority. Common routing protocol. A connected network. There is at least one route between any pair of nodes. Application of IRP and DRP. Intra-as routing. Also known as interior router protocols, IRP, or interior gateway protocols, IGP. Most common. RIP, routing information protocol. OSPF, open shortest path first. IGRP, interior gateway routing protocol, Cisco proprietary. Shortest path algorithm. Dijkstra's algorithm. Shortest path algorithm. Weighted graphs. Shortest path algorithm. Negative weighted graphs. Bellman-Ford's algorithm. Shortest path algorithm. Negative weighted graphs. 6. Yen. 7. S. Z. Y. 8. -3. 2. 9. -2. X. T. -4. 5. 5. Yen. S. Z. Y. 6. 7. 8. -3. 2. 9. -2. X. T. -4. 6. Yen. 7. S. Z. Y. 8. -3. 2. 9. -2. X. T. -4. 5. 6. 4. 7. 2. S. Z. Y. 8. -3. 9. -2. X. T. -4. 5. Bellman-Ford's algorithm. 6. 4. 7. 2. S. Z. Y. 8. -3. 9. -2. X. T. -4. 5. 2. 4. 7. S. Z. Y. 6. 8. -3. 9. -2. X. T. -4. 5. 2. 4. 7. S. Z. Y. 6. 8. -3. 9. -2. X. T. -4. 5. 2. 4. 7. -2. S. Z. Y. 6. 8. -3. 9. X. T. -4. Types of routing protocol. Reactive, on-demand, protocols. Discover routes when needed. Source-initiated route discovery. Example, ad hoc on-demand distance vector, AODV, dynamic source routing, DSR. Proactive protocols, table-driven. Traditional distributed shortest path protocols. Based on periodic updates. High routing overhead. Example, highly dynamic destination sequence distance vector routing protocol, DSDV, optimized link state routing protocol, OLSR, open shortest path first, OSPF, RIP. Routing types. Nodes must determine how to forward packets. Source routing. Routing decision is made at the sender. In source routing, complete route information from source to destination is included in the data packets. Not feasible to the large-scale network hop-by-hop routing. Routing decision is made at each intermediate node. Hop-by-hop routing. In hop-by-hop routing, each data packet contains next hop address and destination address. Routing decision is made at each intermediate node. Proactive routing protocol. Table-driven routing protocol. RIP, routing information protocol. Distance vector algorithm. Proactive routing protocol. Distance vectors, exchanged every 30 seconds via response message, also called advertisement. Each advertisement, route to up to 25 destination nets, RIP, routing information protocol. Z. W. X. Y. A. D. B. C. Destination network next route num. Of hops to dest. WA2. YB2. ZB7. X1. Routing table in D, RIP, link failure and recovery. If no advertisement heard after 180 seconds, neighbor/link declared dead. Routes via neighbor invalidated. New advertisements sent to neighbors. Neighbors in turn send out new advertisements, if tables changed. Link failure info quickly propagates to entire net. OSPF, open shortest path first. Uses link state algorithm. LS packet dissemination. Topology map at each node. Route computation using Dijkstra's algorithm. OSPF advertisement carries one entry per neighbor router. Advertisements disseminated to entire AS, via flooding. conceived as a successor to RIP. Destination Sequence Distance Vector Routing, DSDV. DSDV is proactive, table-driven. DSDV is destination-based. Each node maintains routing information for all known destinations. Routing information must be updated periodically. Maintains routes which are never used. Traffic overhead even if there is no change in network topology. DSDV functionality route advertisements route selection. Advertise to each neighbor own routing information which consist of destination address, metric equals number of hops to destination, destination sequence number, rules to set sequence number information. On each advertisement increase own destination sequence number. If a node is no more reachable, timeout, increase sequence number of this node by 1 and set metric equals. Route selection. Update information is compared to own routing table. Select route with higher destination sequence number, this ensure to use always newest information from destination. Select the route with better metric when sequence numbers are equal. Respond to topology changes. Immediate advertisements. Information on new routes, broken links, metric changes immediately propagated to neighbors. Full/incremental update. Full update, send all routing information from own table. Incremental update, send only entries that have changed. Make it fit into one single packet. DSDV, tables, ABC12 dest. Next metric sec A550 B1 B100 C3 A550 B1 B100 C3 C586 dest. Next metric sec A1 A550 B B100 C2 C588 dest. Next metric sec A B1 A550 2 B100 C C588 DSDV route advertisement. B increases sec dot near from 100 greater than 102. B broadcasts routing information to neighbors A, C including destination sequence numbers. A1, A500. B0, B102. C1, C588. A1, A500. B0, B102. C1, C588. 1. A. B. C. Dest. Next. Metric. Sec. A. A550. B. 1. B102. C. 2. C588. Dest. Next. Metric. Sec. A. 1. A550. B. B102. C. C588. Dest. Next. Metric. Sec. A. B. 2. A550. 1. B102. C. C588. DSDV, new node. 2. Insert entry for D with sequence number D000, then immediately broadcast on table. 1. D broadcast for first time sent sequence number D000. D0, D000. A, B, C, D, dest. Next. Metric. Sec. A 550. B 1. B 104. C 2. C 590. Dest. Next. Metric. Sec. A 1. A 550. B 104. C 590. Dest. Next. Metric. Sec. A B 2. A 550. 1. B 104. C 590. D 000. DSDV, new node cont, ABCD. 3. C increases its sequence number to C592, then broadcasts its new table. 4. B gets this new information and updates its table. A 2, A 550. B 1, B 102. C 0, C 592. D 1, D000. A 2, A 550. B 1, B 102. C 0, C 592. D 1, D000. A B C D dest. Next. Metric. Sec. A 550. B 1. B 104. C 2. C 590. Dest. Next. Metric. Sec. A 1. A 550. B 102. C 592. D 2. D000. Dest. Next. Metric. Sec. A B 2. A 550. 1. B 102. C 592. D 000. DSDV, no loops, no count to infinity. 2. B does its broadcast, greater than no effect on C. C knows that B has stale information because C has higher sec. Number for destination D, greater than no loop, greater than no count to infinity. 1. Node C detects broken link, greater than increase sec. Nearby 1, only case where not the destination sets the sequence number, greater than odd number. D 2, D 100. D 2, D 100. D A B C dest. Next. Metric. Sec. D B 3. D 100. Dest.C. Next. Metric. Sec. D C 2. D 100. Dest. Next. Metric. Sec. D D101. DSTV, immediate advertisement. 3. Immediate propagation B to A, update information has higher sec. Near, greater than replace table entry. 2. Immediate propagation C to B, update information has higher sec. Near, greater than replace table entry. 1. Node C detects broken link, greater than increase sec. Nearby 1, only case where not the destination sets the sequence number, greater than odd number. D, D101. D, D101. D, A, B, C, dest. Next. Metric. Sec. D, B, 3, D100. D101. Dest. Next. Metric. Sec. D, B, 4, D100. Dest.C. Next. Metric. Sec. D, C, 2, D100. D101. Dest.C. Next. Metric. Sec. D, C, 3, D100. Dest. Next. Metric. Sec. D, B, 1, D100. Dest. Next. Metric. Sec. D, 1, D100. D101. Reactive routing protocol. On-demand routing protocol. AODV concepts. 1. AODV, ad hoc on-demand distance vector routing protocol. Pure on-demand routing protocol. A node does not perform route discovery or maintenance until it needs a route to another node or it offers its services as an intermediate node. Nodes that are not on active paths do not maintain routing information and do not participate in routing table exchanges. Uses a broadcast route discovery mechanism. Uses hop-by-hop routing. Routes are based on dynamic table entries maintained at intermediate nodes. Similar to dynamic source routing, DSR, but DSR uses source routing. AODV concepts. 2. Local hello messages are used to determine local connectivity. Can reduce response time to routing requests. Can trigger updates when necessary. Sequence numbers are assigned to routes and routing table entries. Used to maintain freshness of route. Every node maintains 2 counters. Node sequence number. Broadcast ID. AODV route request. 1. Initiated when a node wants to communicate with another node, but does not have a route to that node. Source node broadcasts a route request, RREQ, packet to its neighbors. Broadcast_I.D. Dest_address. Type. Flags. Hopcont. Reserved. Dest_sequence_hash. Source_address. Source_sequence_hash. AODV route request. 2. Sequence numbers. Source sequence indicates freshness of reverse route to the source. Destination sequence number indicates freshness of route to the destination. Every neighbor receives the RUC and either returns a route reply, RREP, packet, or forwards the RUC to its neighbors. Source_address, broadcast_I.D, uniquely identifies the RUC. Broadcast_I.D is incremented for every RUC packet sent. Receivers can identify and discard duplicate RUC packets. A odd route request. 3. If a node cannot respond to the RUC, the node increments the hop count. The node saves information to implement a reverse path setup. A odd assumes symmetrical links. Neighbor that sent this RUC packet. Destination IP address. Source IP address. Broadcast ID. Source node's sequence number. Expiration time for reverse path entry, to enable garbage collection. A odd example, 1, node 1 needs to send a data packet to node 7. 4, 6, 1, 7, 5, 3, 2. Node 1 needs to send a data packet to node 7. Assume node 6 knows a current route to node 7. Assume that no other route information exists in the network, related to node 7. A odd example, 2, node 1 sends a RUC packet to its neighbors. 4, 6, 1, 7, 5, 3, 2. Node 1 sends a RUC packet to its neighbors. Source underscore address equals 1. Dest underscore address equals 7. Broadcast underscore I.D. equals broadcast underscore I.D. plus 1. Source underscore sequence underscore hash equals source underscore sequence underscore hash plus 1. Dest underscore sequence underscore hash equals last dest underscore sequence underscore hash for node 7. A odd example, 3, 4, 6, 1, 7, 5, 3, 2. Nodes 2 and 4 verify that this is a new RUC and that the source underscore sequence underscore hash is not stale with respect to the reverse route to node 1. Nodes 2 and 4 forward the RUC. Update source underscore sequence underscore hash for node 1. Increment hop underscore st in the RUC packet. A odd example, 4, RUC reaches node 6, which knows a route to 7. 1, 7, 5, 3, 2. RUC reaches node 6, which knows a route to 7. Node 6 must verify that the destination sequence number is less than or equal to the destination sequence number it has recorded for node 7. Nodes 3 and 5 will forward the RUC packet, but the receivers recognize the packets as duplicates. A odd route reply, 1. If a node receives an RUC packet and it has a current route to the target destination, then it unicasts a route reply packet, RREP, to the neighbor that sent the RUC packet. Dest underscore address. Type. Flags. Hopcount. RSVD. Dest underscore sequence underscore hash. Source underscore address. Lifetime. PRSZ. A odd route reply, 2. Intermediate nodes propagate the first RUC for the source towards the source using cached reverse route entries. Other RUC packets are discarded unless dest underscore sequence underscore hash number is higher than the previous, or destination underscore sequence underscore hash is the same, but hop underscore st is smaller, i.e., there's a better path. RUP eventually makes it to the source, which can use the neighbor sending the RUP as its next hop for sending to the destination. Cached reverse routes will time out in nodes not seeing a RUP packet. A odd example, 5, 4, 6, 1, 7, 5, 3, 2. Node 6 knows a route to node 7 and sends an RUP to node 4. Source underscore address equals 1. Dest underscore address equals 7. dest underscore sequence underscore hash equals maximum own sequence number, dest underscore sequence underscore hash in ruc. Hop underscore t equals 1. Of example, 6, 4, 6, 1, 7, 5, 3, 2. Node 4 verifies that this is a new route reply, the case here, or one that has a lower hop count and, if so, propagates the RIP packet to node 1. Increments hop underscore t in the RIP packet. Of example, 7, 4, dest. Next. Hops. 7, 4, 3, 6, 1, 7, 5, 3, 2. Node 1 now has a route to node 7 in 3 hops and can use it immediately to send data packets. Note that the first data packet that prompted path discovery has been delayed until the first route was returned. Of route maintenance. Route changes can be detected by failure of periodic hello packets, failure or disconnect indication from the link level, failure of transmission of a packet to the next hop, can detect by listening for the retransmission if it is not the final destination. The upstream, toward the source, node detecting a failure propagates an route error, RERR, packet with a new destination sequence number and a hop count of infinity, unreachable. The source, or another node on the path, can rebuild a path by sending a RUC packet. Of example, 8, assume that node 7 moves and link 6 to 7 breaks. 4, 6, 1, 7, 5, 3, 2, 7. Assume that node 7 moves and link 6 to 7 breaks. Node 6 issues an error packet indicating the broken path. The error propagates back to node 1. Node 1 can discover a new route. Dynamic source routing, DSR. Hierarchical algorithms, 1. Scalability. MANA protocols often do not perform well for large networks, especially if not dense. Global topology is based on the connectivity of each mobile node. Clusters can be used to provide scalability. Clusters are formed, dynamically, of course, to provide hierarchy. Global routing is done to clusters. Local routing is done to nodes within a cluster. Clusters of clusters, superclusters, can be formed to extend hierarchy. Similar in principle to IP subnets, hierarchical algorithms, 2. A special node, called the cluster head, is designated in each cluster, responsible for routing data to or from other clusters. May be a special node, or may be designated through a clustering algorithm. Algorithms. Clustering, form clusters. Cluster head identification, may be an integral part of the clustering algorithm. Routing, some routing algorithm is still needed. Applied at each level of the hierarchy.